Good morning, good afternoon, good evening, depending on where you are. My name is Gerald Verbeek. I'm the moderator of the It's Money webinar series, the 15th edition. And we're very happy that you have decided to join us for this webinar, where we once again will present 3 case studies where additional testing resulted in saving money. Whether it's money directly by using less materials, or because we had a shorter schedule, or we reduced risk, whatever the case may be, we will demonstrate that more testing does save money, and that's why we have this webinar series, It's Money. Before we get started, a few housekeeping notes. During the webinar, all attendees will be muted. Here we go too fast. And there will be, after each presentation, there will be a Q&A. And if you have a question, please use the question box on your screen to convey that question, so that I can then, during the Q&A session, pose those questions to the speakers. The speakers that we have today are Kevin Hetrick from Clark Dietz, Don Davies from Madison Clemensic Associates, and Edward Stehmeyer from the South Carolina Port Authority, who will give you 3 presentations, as I said, on 3 different case studies, 2 dealing with reuse of foundations, and then 1 on an innovative way of reducing the carbon footprint, but also in doing so saving money. And with that, I just want to hand over the controls to Kevin Hetrick for his presentation. Kevin, the floor is yours.
Thank you, Gerald. Let's see here. There we go. Good morning. My name is Kevin Hetrick. I'm the Central Indiana Area Manager for Clark Dietz. I don't know where everyone else is located, but we're expecting a foot of snow here today in Indianapolis. Clark Dietz is a Midwest engineering firm serving Indiana, Illinois, Wisconsin, and Kentucky. Prior to working at Clark Dietz, I was a project manager with the Indiana Department of Transportation. And the project I'll be discussing today was from my time at INDOT. Project is Milton Madison Bridge, a major rehabilitation and reconstruction of an Ohio River bridge connecting Madison, Indiana, and Milton, Kentucky. On the project, extensive pier and foundation testing and analysis during design allowed for pier and foundation reuse, cutting project costs by nearly half. I'd like to start by giving credit to the many project partners who made the project a success. INDOT and the Kentucky Transportation Cabinet were committed to restoring the bridge to like new condition. Many of the items discussed in today's presentation required federal highway approval. The project was eventually procured as a design build. That team was led by Walsh Construction, with Buckland and Taylor as the engineer of record for the truss superstructure, and Burgess and Nipel serving as the engineer of record of the pier rehab that I'll be discussing today. Working for INDOT and KYTC, Michael Baker were our lead technical experts, and many of the ideas addressed in today's presentation are credit to the engineers at Michael Baker. Last but not least, CDM Smith led the environmental process on behalf of the 2 states. Milton Madison Bridge is located approximately halfway between Louisville and Cincinnati, and is a vital connection for the people of Madison, Indiana, and Milton, Kentucky. There are only 2 bridges in the 110-mile stretch of river between Louisville and Cincinnati. Any bridge closure would require a 50-mile detour for the users of Madison and Milton. 2 towns largely operated as 1 town. The users use the bridge daily to go to work, to see their families, to shop for groceries. Closing this bridge is going to be a major inconvenience for the local users. Unfortunately, the bridge is getting very old. When we started working on this project, it was 2009. The bridge was built in 1929, making it 80 years old. As a steel truss bridge, especially in the Midwest, an 80-year-old truss was starting to be in pretty rough condition. It needed routine maintenance, which required occasional closures and detours. And it was the condition of the bridge is a major concern for the locals, but also for INDOT and the Kentucky Transportation Cabinet. You can see a couple pictures on this slide. The bridge was running out of time. Many of the steel truss members were corroded all the way through. The load rating had been dropped to 15 tons. Then just as we were starting construction in 2011, the states decided to drop the load rating all the way to 3 tons. The bridge was also very narrow. I mean, built for the vehicles in 1929. Only 10-foot wide lanes, 20-foot wide total curb to curb. Had a lot of crashes on the bridge. It was a daily safety concern. A lot of side view mirrors being swiped. Looking to provide a reliable crossing for the two towns. In 2009, NDOT and KYTC had undertaken an environmental assessment. Many new alignment alternatives were explored, but also an alternative that was looked at was keeping the bridge on the existing alignment. Keeping the bridge off on alignment offered a path of least resistance, as both Madison and Milton included large historic districts. The Section 106 consultation was extensive, involving parties in both states and Washington, D.C. There are many challenges to keeping the bridge in alignment, though. For one, to construct a new bridge in the existing alignment, the bridge would need to close during construction, which is going to be a big inconvenience for users. Also, it wasn't clear how viable it was to reuse the piers. In 2009, the federal Tiger Grant program came out, which was intended to award funds to shovel-ready projects. For Milton Madison, the superstructure replacement with minimal approaches alternative could be shovel-ready. No right-of-way was required. Staying on existing alignment simplified our NEPA and permitting processes. So the states moved forward with the project as a design build, applied for a Tiger Grant, and received $25 million, with the goal to have the project under construction approximately 18 months later. The existing bridge was 5 spans across the Ohio River. The alternative to reuse existing piers would reduce that to 4 spans. 4 existing piers would be encased with new concrete and strengthened. New pier caps would be constructed, and a new pier would be constructed on the Indiana shore, replacing 2 existing piers. With the pier rehabilitation alternative, the Coast Guard had confirmed that the navigation channel could remain as is, which is a big victory for the project, as a new bridge was going to require a much larger navigation channel, which was going to drive up project costs considerably. While the piers are mostly staying the same as existing, the truss superstructure is planned to receive a major overhaul. Existing 10-foot wide travel lanes with no shoulders would be expanded to 12-foot wide. Shoulders would be added to provide space for broken down vehicles and to maintain traffic during inspections and maintenance. A sidewalk was planned to be cantilevered off the downstream end of the truss. In total, the width of the truss was more than doubling from the original condition. The wider footprint, additional dead load, and eccentric forces from the significantly larger superstructure were a unique challenge for pier reuse. In assessing the viability of reusing the piers, several goals were set to determine what a successful pier rehabilitation would consist of. First, the 2 states wanted a like new bridge. This was a big investment, and we were looking for 75 years of service life. Budget was a big consideration. Could a pier rehabilitation solution provide the cost savings we were looking for to fit within the $100 million budget? Also, the piers could be permittable. The U.S. Coast Guard had concurred with maintaining the 727-foot wide navigation channel, but we had to make sure not to reduce that. And finally, the piers need to be acceptable to historic consulting parties. The city of Madison includes a 2,000 building historic district, and Section 106 consultation was extensive on the project. One challenge to doubling the size of the truss from 24 feet to 48 feet was that the existing piers were tapered to carry a 24-foot wide truss. The new truss was going to require a much wider pier cap. To do that, we're just going to pour concrete shell around the existing pier while the bridge was still in service. Then she construct a new pier cap, remove the truss, and build a new truss on top of the widened pier cap. A lot of the work would be able to happen while traffic was still on the bridge, but eventually the bridge would need closed to reconstruct the truss. Knowing what the end product needed to look like still required a lot of engineering to confirm there was a viable, cost-effective alternative to reuse the piers. The engineers on the project started by researching the original plans, reviewing the 1929 plans, but also reviewing construction photos and press accounts from the time. The foundation of the bridge was constructed as a pneumatic caisson. As shown in the picture in this slide, a steel chamber was constructed on shore. The chamber included 2 airlocks. Once the chamber was completed, it was floated into place and sunk to the bottom of the river. From there, wooden forms and concrete were constructed on top of the caisson. Workers entered the airlocks, and as they excavated material, the caisson sank deeper into the river bottom. This was continued until the caisson sank to the bedrock. The foundation was socketed into the shale bedrock below. With the caisson fully embedded in the bedrock, wood forms were installed from the river's bottom to above the water level. Concrete was poured through the airlocks into the caisson, filling both, after which construction of the pier stem started. It's worth noting that with this construction method, there was no reinforcing in the original caisson, which certainly became a challenge to determine if the piers could be reused. So next step, reinforcing steel was doweled 12 feet deep into the unreinforced caisson. Wooden forms were installed inside the caisson forms, and a reinforced pier stem was erected going up from there. The original construction, as noted previously, there was no reinforcing in the caisson, unless you count the airlocks. The pier stem was significantly under reinforced by today's design standards. Knowing what we knew about the original bridge and how it was built, our team set out to get a better understanding of the current condition of the bridge. 2 cores were taken from each pier, drilling through the deck, the pier stem, the caisson, all the way down into the bedrock. Geotechnical borings were also taken of the river bottom around each pier. The total depth of the cores approached 200 feet in length. The slide shows a small portion of the samples taken from the piers. The top and bottom of the caisson are apparent in these pictures. All samples were sent to the lab for testing. The strength of the concrete was very good. Much of the piers in the caisson have been underwater for 80 years, and some samples approach strengths of 10,000 psi. Chloride content for most piers is acceptable, other than one pier on the Indiana approach had been exposed to years of de-icing. That pier, as previously noted, was removed and replaced with another pier, a new pier, on the Indiana banks. Arm's length inspections were performed of each pier. Crews looked for visual defects that weren't apparent, like spalling, honeycombing, or reinforced steel. And they sounded the bridge to look for delamination or voids. Underwater inspections were also performed of each pier and geotechnical borings taken of the soil in each location. If the pier is going to be incorporated into the new design, both states wanted to ensure that the existing piers were in very good condition. The geotechnical borings revealed that the river soils consist of approximately 60 feet depth of sand and gravel. The layer also featured heavy boulders at the bottom. Bedrock was mostly shale with limestone. The original caisson was socketed into the rock approximately 2 to 7 feet. There's a 70-foot height of unreinforced caisson extending up from the bedrock, and nearly 100 feet of unreinforced pier stem above that. At that point, we'd resolved that the piers were in good condition for the way they were built. Knowing that the piers were in good condition was only a small piece of the puzzle. In addition to building a much larger truss in these piers, modern design loads to be considered were much more extensive than the loads considered in 1929. Those loads included dead load from a heavier truss, modern codes for wind loading, larger live loads and braking loads from today's heavy vehicles, increased weight from new pier concrete, and vessel collision, a factor that was completely not considered in the original design. The engineers on the team also had many concerns to address relative to how the new and old concrete perform in a composite manner. There were concerns with how the bearing loads would act on the widened pier cap. Tension in the under-reinforced stem and the interface with the caisson were definite challenges. And tension in the unreinforced caisson was something that definitely needed addressed. Last but not least, consideration needed given to the underlying soils and their stability to handle the demands. There's a general understanding that designing the rehabilitated piers using standard vessel impact and wind loads would result in expensive foundation improvements that would make the superstructure replacement alternative cost prohibitive. With the piers needed designed to withstand modern load combinations, the engineers in the project worked to determine risk-based loading criteria instead of relying on deterministic load requirements. One method to do that was to use method 2 from AASHTO's vessel collision specification. Between 40,000 and 60,000 barges per year use the Ohio River at Milton, Madison. Close coordination was undertaken with Federal Highway, the U.S. Coast Guard, and the U.S. Army Corps of Engineers to determine the water levels, size and number of barges, and the classification of the bridge for a method 2 barge analysis. Milton Madison was classified as a regular bridge with acceptable annual frequency of collapse of 0.001, the number of vessels, the likelihood of an aberrant barge, the geometric probability of vessel impact, and the likelihood of collapse due to an impact were all considered to determine the required pier capacity that was needed to withstand barge impact. Water levels for various flood events were coordinated with the Army Corps. 2 different barge impact events were considered, and a drift barge floating at the 100-year flood elevation, and the second was a fully loaded barge traveling downstream at mean high water. Results of the study provided impact forces to be used to determine the required pier capacity for vessel collision, as detailed in the table. This table that's taken from the project's vessels collision study. The study provided the project with acceptable risk-based criteria that would provide for a long-lasting bridge while also controlling project cost. Complying with this document eventually became a requirement that we put on the design builder. The other major lateral load that the project engineers sought to refine was wind loading. Towards this, the project contracted with Rowan, Williams, Davies, and Irwin to perform a site-specific wind study. RWDI performed a statistical wind climate analysis to determine site-specific wind speeds using 60 years of available data from the Louisville and Cincinnati airports and 35 years of data from the Lexington, Kentucky airport. RWDI simulated the terrain and surface conditions to develop a 3D model of the bridge site. Directionality of the wind was considered, and turbulence properties for wind in the corridor were assessed. At their Ontario labs, RWDI performed static 2D testing with 3D wind tunnel testing to gain an understanding of the site and also the aerodynamic stability of the bridge. And as a result of the project-specific wind study, we were able to use wind loading that was significantly reduced from the conservative wind speeds required by code. The project-specific wind speeds were able to be reduced by up to 30%, while providing an accurate picture of the conditions that the bridge was likely to be exposed to. 1 hour wind speeds were provided for design loads, while 10-minute wind speeds were provided to check stability. Based on RWI's calculated wind speed and their lab modeling, the bridge was determined to be stable, and the reduced wind loads played a significant contribution to controlling project costs. Having reduced the lateral loads in the project significantly was very important, but providing a suitable design to use a narrow, unreinforced spread footing still offered many challenges. Geotechnical engineers in the project accepted the task of limiting deflection of the pier, keeping eccentricity within the footing, and keeping peak foundation bearing pressures to acceptable thresholds. Using conventional analysis, meeting these criteria was not feasible without extensive foundation improvements. Ideas that were under consideration were major soils improvements around the piers, installing pipe pile upstream and downstream, and connecting those to the caissons. Another alternative that was proposed was to analyze the hours disregarded, as it may not be in place when needed to withstand the extreme loads. Due to the softness of the surrounding soil and the variability of the soil response based on pier deflection, the resistance to the surrounding soils are typically left out of a conservative analysis also. This results in a simple spread footing on rock. In the case of Milton, Madison, that resulted in force resultants with eccentricity of over 20 feet, which was a problem because the caisson was only 20 feet wide. To address this, the engineers at Michael Baker proposed using finite element analysis that considered the response of the soils in supporting the pier and foundation against lateral loads. This was coordinated closely with Federal Highway, and a scour mitigation design was approved that would keep the surrounding soils where they were needed to improve foundation resistance. The proposed scour mitigation consisted of placing a 12-foot thick riprap shelf below the contraction scour depth. The depth and thickness was selected to avoid turbulence and to avoid being undercut by bed forms. High performance geotextiles and large riprap were specified to resist local scour. The soft soils surrounding a spread footing are typically disregarded as part of conservative design practice. With the assumption that surrounding soils remain in place to improve foundation resistance, however, the loads of the bedrock were significantly reduced. This slide shows the load resistance with no surrounding soils considered and with the surrounding soils included. In the former scenario, the bedrock carries all the load, becoming very eccentric, resulting in overturning. With the soil considered in the analysis, as the pier deflects, the soft soil provides increased resistance, reducing the load in the bedrock. This more closely matches reality. The resultant load stayed within the foundation limits. The engineers at Michael Baker performed 3D finite element analysis with Midas GTS software to model the responses of the pier, caisson, soil, and rock. The soil and rock are modeled with more Coulomb failure criterion. The pier is modeled as an elastic solid, and the interfaces between the pier and the subsurface are modeled as standard friction interface. Here's some screen caps of that. The results of the analysis showed acceptable performance for the foundation. Maximum bearing stresses were less than the project's design criteria. Deflection of the pier stayed within the project's goals. This foundation never goes into tension, and eccentricity was determined to be acceptable. Determining that the existing soils and foundation can withstand modern loading demands was a huge hurdle cleared for the viability of cost-effective pier reuse. The next challenge was to transfer the loads into the soils and foundation. Two concerns to be addressed included tension in the under-reinforced stem and at the interface between the stem and the caisson, and also tension in the unreinforced caisson needed to be addressed. This slide shows compression and tension forces developed in the pier and caisson for various load combinations for the new widened truss and piers. For service load combinations, the pier and caisson tended to remain in compression. For various strength and extreme event load combinations, the pier and caisson entered tension. To provide for 75-year service life, a variety of criteria were established for tension in the pier. These included goals of no tension for any service limit state and tension less than 95 psi for strength and extreme event load combinations. Wherever those criteria were not met, the caisson or stem would be strengthened and reinforced with reinforcing steel and a concrete shell. The strengthening would continue beyond the limit of the tension, plus the development length of the reinforcing steel. This sketch shows the pier strengthening that was eventually proposed. The proposal to strengthen the pier and holes would be cored deep into the unreinforced caisson with bundles of reinforcing steel grouted into the holes. Stem reinforcement would be continued onto the retrofitted caisson reinforcing, and a 24-inch minimum thickness high-performance concrete collar was installed around the existing pier stem. Final challenges to address include ensuring that the new original concrete would act as a composite structure. The pre-existing piers were supporting the weight of a 24-foot wide truss and would continue carrying that load throughout the construction of the pier encasement. With the existing truss removed, the previously loaded pier concrete would have a tendency to relax, creating interface shear between the new and old concrete. With the superstructure loads imparted through the bearings into only the widened pier cap, the new and old material would need to act in a composite manner to withstand these forces. To address these concerns, post-stressing was performed to the pier cap and stirrups were doweled into the existing pier throughout the height of the structure to provide composite performance and withstand shear forces at the interface. All right, I think I'm doing all right in time. That was a lot of discussion about the engineering that went into coming up with the solution of the project, or how to reuse the piers in the project. This project was built almost a decade ago. Technically, the substructure work that we're looking at here probably did happen about a decade ago. Construction was 2011 to 2013. I got some construction pictures here. This is down in the cofferdam. Looking here, I mentioned holes being doweled deep into the caissons and bundles of reinforcing steel being grouted into those. It was 3 number 14 bars that were bundled together at 3 feet spacing that got grouted into the caissons. One interesting thing that happened was that as Walsh was coring those 4-inch holes, the ties for the original caisson form were steel I-beams. So a rather unexpected thing that caused him to go through a lot of drill bits and take a lot of time was drilling through I-beams as they went down in those 4-inch core holes. It's a lot of coring too, approximately 70-foot deep caisson, I think 55 holes around the length of the caisson. So over 3,000 feet of drilling through concrete and steel beams. Here's a picture of the pier stem coming up from the caisson. I mentioned concerns about the interface between the new concrete and the old concrete and how that would react. Stirrups are basically specified to be installed at 2 feet vertical spacing and approximately 1 feet horizontal spacing the entire length of the existing pier stem to make sure that the new stem and the new concrete encasement and the old stem acted in a composite manner. Here's a picture coming up from the water. As mentioned previously, the original pier stems tapered inward to carry a 24-foot wide truss. The new pier stem was going to be a uniform shape up into the new pier cap, which would flare out. And then this is a picture of a mostly constructed pier. Again, the pier cap flares out to carry the 48-foot wide truss. It's also worth noting, and you may be able to see here, that they built the pier cap, left one piece of it incomplete. That was for a maintenance of traffic alternative that our design builder proposed as part of the selected team. It's kind of a side note to this presentation, but also one of the most fascinating aspects of the project. We procured this project, INDOT and KYTC did, in September 2010. And at the time, we were planning on the bridge being built, basically the substructure being constructed while traffic was still running on US 421. And then eventually the truss would be removed and a new truss constructed on top of the reconstructed piers. We're allowing design builders to have up to 365 days of closure to do that, but we also incentivized shorter construction or closure timeframes. I think at the time we'd done $25,000 per day for every day that they could shorten the closure timeframe. 4 of our 5 bidders bid 365 days. The 5th company, Walsh, bid 10 days, which we knew they were going that direction, but their proposal was to build temporary piers adjacent to the bridge, support the new truss or build the new truss on the temporary piers, eventually route traffic onto that before finally demoing the existing truss and then sliding the new truss into place. It was an extremely fascinating idea, amazing engineering on behalf of the Walsh and Buckland and Taylor and Burgess and Nipel team. And I do have a quick video to show of that. This is the bridge slide that was performed. Basically, as I mentioned, they had traffic running on that bridge on a temporary alignment. You can see the temporary foundations that they had constructed next to the permanent foundations. And actually, the foundation of the bridge was half temporary, and then they rested half of it on the new pier construction, eventually shifting traffic over onto the new truss on the temporary alignment while they demoed the existing truss and finished their pier caps before finally doing this. This was basically pulled into place with equipment that would normally be lifting equipment. Ton of amazing engineering done by this team to make this work. I believe the 15,000 tons was the weight of the truss. 30 million pounds is what they pulled 55 feet into place to this happened over the course of, I think, a little less than a day, if I recall. My memory is a little rusty. It's been 10 years at this point. But overall, an extremely fascinating project. I think that it was an amazing project from the beginning. Of all the concepts I talked about today with reusing the piers and the work that went into even being able to bring forward a project that was literally able to reduce project costs by close to half to reuse those piers and keep the truss on the existing alignment. But then certainly getting into construction and having the design builder propose this specific maintenance of traffic scheme definitely took the project to completely new levels. So thank you for the opportunity to present today. And I guess I need to move to the next slide. I think my half hour is about over. Gerald, that's the end for me.
Thanks, Kevin. Thank you very much. And I'm very pleased that we finally had the opportunity for you to present this project. Yes, it's part of its money, but the final part on sliding this truss into place was definitely made it worthwhile. Before we go to the next presentation, I have time for one question, and that's something that we will talk about more in the Q&A section as well. But obviously, for this project to take place, an awful lot of testing had to be done. A lot of concepts had to be investigated. And I think it's, listening to you, if the Coast Guard had said, hey, we can still with a new alignment, you don't need to do anything major with regards to the route in the river. If they had been more flexible in it, do you think that we would still have had a reuse of these trusses, or was it, or the supports, or was it more because of what the Coast Guard initially told you, you had no choice but to reuse the existing foundations?
No, I think even if there was more flexibility, we would have ended at this alternative. I mean, certainly as we went through the analysis of reusing the foundations, the most expensive alternatives that were under consideration to reuse the foundations were not needed because of some of the finite element analysis and some of the load reduction that was able to be done. So really, I mean, the project cost did drop. I think replacement was looking at $160, $170 million. We ended up bidding this for $104 million. So no, even if we had to, or were able to keep 727 feet for new bridge, this alternative ended up being certainly the most viable, cost-effective project alternative.
Okay, fair enough. More questions during Q&A. To stay on time, I just want to shift now to a completely different type of project, different kind of case study presented by Don Davies. Carol, if you could give Don the controls, and Don, let us hear some more about testing and carbon and then dollars. The floor is yours.
Thank you very much. And making sure I have control of the screen here. Yeah, I do. Okay. So I'm going to pivot us a little bit here. And so just quickly, myself, Don Davies, I'm the president of Madison Associates. We're a 200-person structural and civil engineering firm. We're in Seattle, but we work across the country and the globe. And I'm mostly going to talk about some Midwest projects here. But more than anything, I want to reframe the conversation here and focus on two key topics. Frankly, how our clients today are looking at what I'm going to call double bottom line decision making, looking at cost and carbon footprint together. And I want to try to help describe for you how we can start bringing embodied carbon into how we talk and show value to our clients of what we're doing. And I'm going to take you, I'm also going to walk you through a series of case studies of some specific projects of ours, looking at where there's, through testing, time, dollars, and yes, carbon were all saved. And the key to that, that's not a 2-for-1, that's a 3-for-1 value message. Personally, I spent a lot of time in my career of late on embodied carbon, and this is an exciting topic. And I'm not saying that just to be patronizing to the group here on the phone or in this call. We have an ability to make an outsized influence on reducing carbon on our projects with really some pretty simple actions based on improving our understanding of the variables we're working with and improving our quality control. You know, better quality control and testing is the easy low-hanging fruit for making an outside difference. And yes, that's about dollars, but it's about carbon. And I know I'm speaking to the choir on this front, but let me give you a few data points on what I mean, and I think how we can also start to talk about this. So what do I mean when we talk about embodied carbon? In fact, what does the term even really mean? We're in a time of change. As the global population urbanizes over the next 30 years, there's a projection for about a 30% increase for the level we are building today in our cities. Now, I don't know if that number is right, or if the statistic of 3,600 more buildings per day in urbanized areas by 2050 is the right number. You know, maybe the population won't move into the cities quite that fast, but these are big numbers. And sorry, I'm having a little short time in getting this to move right. But in order to meet this effectively, what I'm going to call an unlimited demand, we have an unlimited amount of resources. Now, according to a 2021 circular economy report 45% of global materials annually extracted from the planet go towards the built environment. So we need to more thoughtfully consider how we use our limited resources. And as creators of the built environment, we're both at the core of our problems and our solutions for how we choose to act on climate change. Now, if you think further about the materials, waste is often 10% of a project budget or more. And that's before we talk about what is or is not being recycled. And certainly foundation systems are one of those places where perhaps waste is one of the greatest amounts that happens during construction. Consider those numbers for a minute and then think about that a contractor's profit margins can often be under 5%. And certainly when we're looking at the end of the life of a project, well in excess of 30% of what gets taken down is often not reused. Frankly, the last presentation is a great example of, how can we do more with what we already have? But when we do take things down, a surprising amount does end up all going to the landfill. So 38% of our built environment, of our total global emissions, if 38% of that is in our built environment, what are we going to do and how do we act on that? And maybe one last bullet point here to think about, the clients that are, at least in the built environment of the buildings that we do, the clients and the tenants moving into these buildings, they're making a lot of ambitious climate pledges. Often they really don't know how they're going to achieve these goals, but they're turning to those expending the most carbon in creating their infrastructure needs. And they're turning to us and saying, what can we do to help them towards their goals, to show movement and action towards those? So embodied carbon and progressive action on showing how to reduce it is becoming a differentiator of who's getting the projects. Gerald, I see a hand up.
Sorry about this. Not intentional.
Okay. So remember this, if nothing else, you can't manage what you don't measure. And I think that's really an ultimate part of what we are talking about here. So in the DNA of embodied carbon tracking on a project, it really comes down to three things. It starts with the material quantity estimate. What are the materials going into the building? As a design team, do we know these? Are we tracking them? How well do we report those out? There's a lot of focus these days. And it's not showing. Oh, there we go. What I'll call environmental product declarations that are coming out, basically like a nutrition label that goes with the material. It reports the amount of carbon or the global warming potential in the materials. Concrete, steel industry, these are much more prevalent these days. And ultimately that becomes a total amount of embodied carbon that goes into a building. This is how the design teams are talking about the information. And it comes a lot, especially into our above grade structures. We're not really talking a lot about it on foundations, but this is a conversation that's coming quite a bit more. Now, tools like the embodied carbon and construction calculator, just to give you a flavor of how fast this topic's moving. This is a national database of these environmental product declarations that was launched about 2 years ago to make the information publicly available. So it puts all these EPDs for different materials in one place. In 2 years, we've gone from 800 to over 45,000 EPDs for the concrete industry alone in this national database. It's a very quickly moving topic. It's getting a lot of buzz. And questions are starting to be asked about this double bottom line accounting, cost and carbon. And so just reiterating what I was saying, this I think is coming more to our foundation systems to talk about double bottom line, bringing carbon into the conversation. And I think whole building LCA is how we talk about the whole project, but foundations and excavations are certainly where it's coming up next. And again, this is just giving flavors of the type of evaluations and the graphics that people are using right now to help describe to owners what the carbon footprint is that's going into their buildings, and then helping devise strategies of what we do about it. And so this is where testing and just looking through quality control, how we can reduce that carbon footprint, huge home. So carbon reduction opportunities, what can we be doing about that when we're talking about our piles? Now, certainly one is find the 2-for-1s, find the 3-for-1 systems. When we put a system into place, make it do a job more than once. Now, this isn't testing, but if we're putting a lot of piles into the ground, using geothermal piles for heat exchange to where there's a more stable heat source or a cooling source at depth. I think the Google project that was just one of their recent projects just being completed in the Silicon Valley area, every single pile is I think it's the world's largest installation of geothermal piles in the world is just being finished right now. Now, the first thing that goes to my mind, I'm looking at all those empty pipes going up and down this pile. What could we do with that for testing to validate integrity of that pile actually before we filled it up with a fluid that we're using it for thermal heat exchange? Something to think about maybe for a later conversation. Recycled use of materials, steel pipe piles. This is the T-Mobile Park where the Mariners play in Seattle. That entire project sits on concrete filled steel pipe piles, but all of the steel for those piles came as a contractor bidder alternate design, where it turned out that there was a oil gas line that had been procured, fabricated, but didn't actually go into place. So there's a whole bunch of steel, very specialty diameter and wall thickness of steel for this gas line that never went in. We ended up redesigning the foundation of the building to reuse that same material. So instead of scrapping that pipeline, remelting it and putting it someplace else, we went and used those. And in fact, those became the pipe piles for this project. Reusing materials whenever possible. I love the last example on repurposing the bridge versus just starting out new. There's a carbon narrative to tell in that, in addition to just the cost savings, and clients are going to be very receptive to those narratives when we can tell them. Now, when we talk about concrete, without question, it's one of the biggest places there's a carbon sink in what we're doing with the built environment. And it typically comes down to the cement. What can we do with the cement? There's new types of cement coming out, type 1L cement, which it's a limestone blend. It's still a type 1 cement. The ASTM designation for it is C595. It ends up being, sorry, the touchy here on the mouse. It ends up being about a 15 to 20% reduction just if we change to type 1L cement. You know, the other big variables that go into making ready-mix concrete, other cement replacements, fly ash, slag, glass powder starting to be used and talked about more. But I want to talk about for a moment about aggregate. It is the biggest by volume component that goes into making ready-mix concrete. And quality control of the aggregate supply is a huge opportunity to reduce the carbon footprint of the concrete going into any of our elements. And I'll use an example of a project in LA that we recently did, where simply by tightening up quality control at the batch plant, tightening up the aggregate in the LA market, there's a very poor aggregate supply. It's very inconsistent. And so the way that the ready-mix industry has solved that is they just put more cement in the concrete to make sure they make the strength that we need as the structural engineer. But if we just study that for a bit, we change the aggregate source to a more consistent imported higher quality, in this case, quartz pea gravel orca aggregate that was being barged down the West Coast. We went from the red bell curve to the blue bell curve. And the end of the day was, even including after shipping the rock down the coast, was a 24% carbon reduction on the project at no cost increase. And the reason it was no cost increase is, yes, it was expensive rock, but rock is cheaper than cement. And for the same volume of ready-mix concrete, the supplier figured out that by using the better quality rock, taking cement out, they could save money and create a lower carbon footprint mix. It still met our design performance characteristics for the strength of concrete we needed. That's the win-win scenarios we want to find. And that's an easy idea that could totally be translatable over to the foundation elements. Key with this, through quality control, through better testing, we can lower our carbon footprint. And so, of course, that moves into not just the material, concrete, and it's the purpose of most of this conversation. We can talk about piles and deep foundation elements. Too often today, what we will do is preliminary design, and then we'll go out and do testing to validate it. And then we immediately move into production with some amount of validation testing for what gets put into place. When we do that, we are doing testing to ensure the integrity of our final design, but we're not really taking advantage of that to optimize the design. What really needs to happen is we need to do more testing earlier, and there needs to be a do loop in the process. We need to do testing, we need to get the values, and there needs to be time that allows us to go in and refine and optimize the design, and then come back with a finalized, more optimal solution based on what we discovered or found out through that initial testing. I know this group would know that, but getting the testing done earlier so that we actually can react to the information we get, it is probably one of the biggest things that is missing often in our foundation elements to truly take advantage of the information that you guys have to offer when we do more testing. Now, ultimately, I advocate this a lot on our projects when we can, is go more to a performance-oriented procurement process where we as designers tell you the information we need and then get out of the way and stop trying to be the experts on things we are not the experts on. So like as an example with foundation elements, especially where there's a number of different proprietary systems and there is, depending on the equipment that someone has, their ability to what they can put into the ground. You know, if I simply put out there the criteria, hey, I need an element at this location with this capacity and this deflection criteria, put that out to the market early enough where we can react to it. And we should be asking back, tell me how much it costs, tell me how fast you can put it in, and tell me the carbon footprint that goes with your system that would go into place. Do that type of double and triple bottom line evaluation as a performance process, and then bring the design build contractor into part of the team as we complete the design. That's usually where we get the best and the highest, both the highest performing, but also the lowest carbon footprint and cost solutions. So let me walk you through a couple of case study projects of buildings that we have recently done to tell some of these stories of exactly what we've just been talking about. So this project here, it's a 34-story apartment tower in Milwaukee called 777. It has 16-inch diameter concrete filled pipe piles. We did both static and dynamic testing during the design phase to change the factor of safety on the piles from 3 down to a factor of 2. Now, the decision for the testing happened in schematics. The actual testing happened near the end of design development. We had results in hand early in the construction document phase, which gave us time to then adjust and iterate the final design before we finalized the project. You know, the test piles were retested about a month after they were put in to allow for both geotechnical capacity set up and for the concrete in them to reach strength. The upfront testing in terms of just pure concrete rebar and steel savings ended up being about $2 million and 6 weeks off the schedule as confirmed by our geotechnical engineer. Adding another layer to that conversation, that was about 1.5 million kilograms of carbon saved, or the equivalent of 340 cars taken off the road for a year just by doing that early testing. That's dollars, time, and carbon reduced through testing that happened during the design process and then taken advantage of before we finalize design. That's a win, win, and a win, all three together. Now, next project here, this one is actually underway right now. This is a 35-story, million-square-foot office tower in downtown Cleveland. Project name's under an NDA at the moment, but if you're from Cleveland, you'll probably know which building I'm talking about. Drilled shafts are up to 8.5 foot diameter, and they're up to 200 feet long under the core of this building. Couple things. We did a method shaft. The sacrificial method shaft was drilled to confirm the large excavation for those shafts could be completed without the need for permanent casing. Now, in the method shaft, the shaft excavation was monitored for both plumbness and consistency through of cross-section through thermal integrity profile testing and sonic logging of the excavation under the slurry to help validate that plumbness and consistency of the cross-section. And then after the method shaft is done, we also cored it, or will be coring it and testing that for the concrete. Once confirmed, we look to be saving 5 million pounds of steel by eliminating the permanent casing through validating, proving that we can do, that the team will be able to do what they say they're going to do. That's about 4 million kilograms of carbon saved. That's equivalent of 900 cars being taken off the road for a full year by doing this additional testing. And that method shaft is actually happening right now as we speak. And so moving to a couple of projects that we've done in Chicago, this is our 150 North Riverside, 52 stories, 1.3 million square feet. It's right on the Chicago River. The project's very aggressive design where it's only the core that is touching the ground of that whole office tower. Would not have been possible without substantial exploration and of the site and knowing where the bedrock is, knowing exactly the capacity of what we had in the foundations before we founded the tower on it. So we had advanced cores into rock for each of the 18 rock socketed caissons. And we did that to confirm at each caisson rock quality and capacity. Here we took the caissons up to a 400 KSF bearing capacity of each shaft. This occurred before the design was finalized, giving us the opportunity to tune the final design, including shaft lengths within their final capacities. And the project also had a substantial podium of H-piles and micropiles. Those low test elements were up to 300 tons. Total, we saved about 1 million pounds of steel in the piles and the H-piles just through the testing that we were doing. Sorry, my image went too far there. That was about 800 kilograms of carbon reduced on just the H-piles and the micropiles only. So, you know, again, a win-win scenario of dollars and carbon. And then lastly, I want to talk about our Vista Tower in Chicago. This is 1,200 feet tall. It's the world's tallest building designed by a woman. It's Jeannie Gang of Studio Gang Architects. And just talking a little bit about the foundations there, it's founded on rock socketed caissons. The bearing capacity of these through Osterberg load cell testing, we went up to 500 KSF. And we actually couldn't go higher than that because uplift forces on the tower started to control more than compression. But after method shaft validation, total project savings of materials, especially by being able to also minimize the amount of permanent casings, was about $1.3 million and about 1 million kilograms of CO2 that was saved. So just finalizing what we're talking about, testing saves dollars, it saves carbon, and it helps reduce risk. And I think this is a win-win scenario that the more you can bring this into your narrative of how you explain what you're doing to people, I think it's just another variable for a win-win-win conversation that should always come out. And at that, let me stop and take any questions you guys might have.
Don, thank you very much for that presentation. As a member of the Testing Evaluation Committee, Obviously, the fact you promote testing is near and dear to my heart. As chair of the Sustainability Committee, I'm obviously even more excited about what you just say, what you just mentioned in here, saving carbon is as well. And then when you put everything together, I think it is indeed more than just a win-win situation. One question that I have before we do the last presentation, and we'll come into more detail during the Q&A, is your thoughts about something that you mentioned earlier. If we do testing earlier in the project execution to really learn from the test results and then optimize the design. Makes sense, obviously, but do you see a change there? Do you see that being more applied, or do you see that people are still reluctant to go that route and then try to move testing earlier in the project execution phase?
There's a reluctance because there's a reluctance of developers to spend dollars early because it's their speculative money before they have the full construction loan for what they're going to do. And so sometimes early dollars are harder to get than later dollars. I think it really takes an advocacy by the design team, by the design professionals, to push our clients to do that testing. And what we need to do is a better job of explaining to them the value of why they should be doing that can be achieved by doing that testing. And you know, so I'm trying to bring in the variable. Let's talk about it from a carbon perspective. Of course, there's always the dollar perspective. We also need to bring in a conversation of risk, and that sometimes is some of the biggest motivation for our developer clients. We need to be able, kind of on each of those hot buttons, explain to them why doing the testing can help improve what we're doing. You know, early dollars to developers, like I said, are precious, but they're ultimately business people. We need to make the business case why doing this additional work is in their financial interest. And then if you make a good case for what you're doing, that's usually where we succeed in getting that early testing done. I mentioned risk. Part of that is because we do a lot of work on the West Coast, and there have been several high-profile projects where during the construction process, things didn't go as expected, whether that is machines breaking down, whether that is surprises in the materials at depth, whether that is quality of what the contractor and the foundation contractor was able to do. All of them cost the owners substantial time and money. And we've, and especially I'm saying in high seismic locations because the density of the rebar and the size of some of the elements down low, all we have to do is show them what happened to the project next door that had a really bad problem and how they don't want that on their site. So God damn it, you got to do X, Y, and Z testing. And we've had a lot more success, but it takes that early advocacy and making the business case to our clients why they need to be doing this. And that's what we need to be better at doing.
Thank you for that. I appreciate it. More questions later. Carol, if you could shift the control to our last speaker, Edward Stehmeyer will give a presentation about a port project. Edward, the floor is yours.
All right, so good day, everybody. My name is Ed Stehmeyer. I'm a general manager of projects and design with the South Carolina State Ports Authority. So you started off the webinar with bridges, you moved on to buildings, and now you've got marine structures. So there's definitely something here for everybody in this presentation today. The topic I'm going to present to you today on is the in-situ dynamic pile testing to realize wharf renovation savings. And hopefully, as we move forward, you'll be able to see what we're talking about here. So let me see. All right, so a brief presentation outline. I'll start off with an introduction, move through the project goals and existing site conditions, talk about the actual testing that we did, the subsequent results and analysis, And the interesting thing that a lot of people talk to us about, especially on this project, was the estimated construction savings, not only in dollars, but also time, and talk about construction successes, and then end up with some conclusions. So this is a photo of the Charleston Harbor. I'm not sure if y'all are familiar with Charleston, but we are located in the east coast of South Carolina. We have a number of facilities that we own and operate in the Charleston Harbor. The one that we're going to be focusing on today is on the right, the Wando Welch Terminal. So the Wando Welch Terminal is actually located in Mount Pleasant, South Carolina. So basically across the river from the Charleston Peninsula. It's over 250 acres. We've got ship-to-shore cranes on the dock. Actually, before the project started, we had 10. And as of now, we actually have 15. So we've been growing by leaps and bounds. Actually, part of my slides cut off. So the approximate capacity. So before we really started this project and a lot of the improvements that we made, the capacity was about 1.6 million TEUs. And around now, we've got a capacity of around 2.4 million TEUs. Normally, when I make these presentations, I always have a quiz question. What is a TEU? So a TEU stands for 20-foot equivalent unit. So anybody who's ever been dealing with the port industry and containers and stuff like that, there's standardized sizes. So they're either 20-foot long, 40-foot long, or 45 feet long. So a TEU is a 20-foot equivalent unit. So just a little bit of quiz knowledge for you today. So our project goals, when we started this out, this wasn't one thing. It was a sort of a collection of things that we saw in the industry that sort of drove us in this direction. Ships are getting faster. Ships are getting larger and larger at a very fast rate. So we had several different objectives, and we're only going to talk about a portion of it today. But we were looking at deepening the Charleston Harbor, which is underway now and should be done later this year, to minus 52 feet mean lower low water. It's about a 7-foot deepening. In some areas, it may be more. We're also looking at servicing these larger vessels. In the bottom left corner, you'll see the CMA, CGN Theodore Roosevelt. So that 20-foot equivalent box I was talking about, these ships can carry upwards of 15,000 TEUs of containers on the vessel. Whenever the Wando Welch Terminal was originally developed, it was suited for more like 4,000 or 5,000 TEU vessels. So that's a substantial increase in vessel size. As a result of that, we also have to increase our crane capacity. I'll talk in detail about that today and sort of how that resulted in the renovation that we're looking at. As a result of that, we got bigger ships coming in. We also have to increase our container storage capacity and throughput on the land side, and increase productivity through the gates and all that kind of stuff. We're going to skip over that today, but I want to sort of give you an idea of what we're looking at. So if we focus mostly on the ship-to-shore cranes, I'm not sure if y'all have ever seen this operation or not, but all the containers are stacked on the vessel itself, and we use ship-to-shore cranes to reach out, pick that container off of the vessel, bring it onto the dock, put it on a truck, and it goes into the yard. Whenever we started this project off in 2015, we had primarily 115-foot lift height cranes. So if you look off to the left, there's 115 feet in between the hook or the grappling hook where that crane actually connects to the container, all the way down to the top of the wharf deck. That's 115 feet. This is just showing, like I said, a typical condition of the Wando Wharf that we started with. Now, we knew with these larger vessels coming in that as they get larger, they not only go deeper, they also get taller. So we had to, through a pretty detailed study, we realized that we needed at a minimum 155-foot lift height, as opposed to the 115 that we originally had. Whenever you do that, you go to 155-foot lift height. That obviously causes a whole bunch of issues, like you heard in the bridge design example earlier. We had all kind of different loading increases, not only from just the crane being heavier, but also as you get taller, the wind forces also get bigger. So we had increased wheel loads and increased tie down loads. In South Carolina, on the East Coast, we obviously also have hurricanes to worry about. So as you get taller, the wind force gets taller, the wind force gets higher. Also increased our tie down loads for securing the crane to the dock during a hurricane. So we actually had, as a part of this project, we had 4 new cranes that we purchased and in service in between October 2016 and July of 2018. We also raised 4 of our existing cranes 40 feet each And those were completed in November of 2018, just to give you an example of outside investment that are going on besides what we're about to detail here. So our cranes also are interesting in the sense that when they come to us, they're actually lowered down. We have this is the Arthur Ravenel Bridge in the Charleston Harbor. So as they come to us, they're actually lowered down, and they are brought to our site. You'll see it sort of in the middle of the picture there. They're brought on vessel. They're offloaded onto our wharf, and then they will look like this after a couple of months. You can see the height difference in between those two there. We showed it in one picture earlier, but this is definitely a visible change. Not only the nicer blue new paint job on the left, but also you can see the lift height in between the booms is definitely different. And that's the 40 feet that we've been talking about. Now let's look at the existing site conditions. Now we know kind of what we're dealing with as far as looking at ship to shore cranes and higher loads as that results. So we also had to deal with the fact that this is an active terminal. The wharf itself, berths 1 and 2, as you'll see in the green and blue, were built back in 1982. They were founded on 18-inch pre-stressed concrete piles with a pile cap and one-way reinforced concrete slab construction type. Berth 3 was built back in 1994. It was founded on 24-inch pre-stressed concrete piles and a two-way reinforced concrete slab. And as I mentioned, the sizes of the vessels have been changing over time. I say it's berth 1, 2, and 3. Whenever these berths were originally constructed, it was suited for 4 ship parking spaces as opposed to 3. So the overall wharf length is 3,800 feet. So four parking spots there. You can imagine the size difference in the ships that are coming in now when we have to narrow it down to just 3 parking spots for the wharf. So this is again a wharf cross section. Let's talk about the existing site conditions. You've got, like I said, a marginal wharf where you've got an existing slope underneath this wharf. Again, it's pile supported. The existing slope itself had armor stone on it in certain areas, underlain by soft organic silty clays. And then the Cooper marl, which I'll talk about in more detail in just a second, is really our foundation layer that we're trying to get to with all of these piles. You can see also off to the left, we were authorized dredge depth of minus 52 feet. So there's a lot of work going on there to not only improve the topside structure, but also the berth and access channel outboard. So the Cooper marl formation, let's talk about that for a minute. It's a firm to stiff clay. It's like I mentioned, it's our typical bearing stratum for deep foundations in Charleston. Getting into details a little bit, it's an over-consolidated, highly plastic clay, or silt, if you want to sort of categorize it that way, with an over-consolidation ratio between 3 and 6. We have a very high undrained shear strength values. This is your SAT word for the day. That we're geologically classified as fossiliferous. Say that one 5 times fast. A fossiliferous limestone. We have the interesting thing about this is anytime you do a CPT sounding in our area, you can definitely tell where it is because you'll get a spike in the excess pore water pressures during the CPT soundings. What you're basically doing there is you're breaking the cementitious bonds or shearing the clay in that instance, and you get an increased pore water pressure as a result. For pile installation, it's a very nerve-wracking thing, and I'll show you why in just a minute, but the pile setup with time, you can actually get a 600 to 800% increase in the capacity whenever you look at the end of initial driving to final design conditions, if you will. So this is the good stuff, but again, I mentioned it's definitely, it can be sort of nerve-wracking to use this material in some instances. So as I mentioned, we're trying to do these renovations to an active terminal. We had to deal with a phased approach inside of the crane rails to do this testing. And I'll explain why we decided to do the testing in just a minute, but we have ship to shore cranes on crane rails that must stay active during the testing and construction. So we have 2 phases. Phase 1, which is off to the left, that's in berth 3, where we will be testing the existing 24-inch pre-stressed concrete piles. We had a closure of 74 days of this small area, and I'll show you what that area looks like in just a minute. Phase 2, we worked in berth 1 on the 18-inch pre-stressed concrete piles that were used as a foundation there, and we had a shorter closure of 33 days in that area. And we gave the contractors approximately about 3,000 square feet up top on top of the wharf, as well as some waterside access where we had all the barges staged outside of our berth, so it didn't impact vessels coming and going to the wharf. So let's look at berth 1 first. As I mentioned, this is a phased approach because we couldn't shut everything down or have contractors working on both sides at once, because it actually shortens the length of your wharf if you do that. And we had all the barges staged outside. If you noticed in the figure, the sort of the purple 50-foot by 120-foot barge staged outside of the wharf, as well as the barge, excuse me, the berth itself. We gave them about a 50-foot, excuse me, a 60-foot wide by 50-foot area on top of the deck to work. And you'll see what that looks like in just a second. And again, this was closed for 33 days. This is just a topside view of what it looks like. You know, it was wide open at the time of this photo, but in general, if we have operations going on, you've got trucks parked there, or even containers or hatch covers put down in these areas. So anytime we were testing in this area, we were losing operational space. So the demolition extents, as you'll notice, the P2 and A5 off to the right are actually where the crane rails are. So we were actually in the middle of the wharf. And we tested 2 interior piles. You can see the hatched area there is what we ended up demolishing out to gain access to 2 18-inch pre-stressed concrete piles. So we tested 2 on either end. So if we look at berth 3, very similar situation. You have 50-foot by 60-foot work area. Same situation when it comes to the barge staging and whatnot, but the construction was different. So the actual work area closure time was different because of the reconstruction. So we're doing all this demolition to get to these piles, but we also have to do the reconstruction to get things back up and running. So looking at the demolition extents in berth 3, since this was a 2A slab, we ended up using a smaller demolition area around to get access to the piles, but we had to use steel strong backs and W36 beams on top of the deck to spread the load out to adjacent piles and crane beams. So again, we couldn't take the ship-to-shore crane rails out of service. So we tested the interior piles, if you will. And I'll show you that in just a second in the section view. But that's, again, why we had a longer closure time. And this one just because of the construction differences and the reconstruction duration. All right, so let's start taking the stuff apart. If we're looking at, this is berth 1. This is the 18-inch pre-stressed concrete piles with a pile cap and one-way slab construction. As you can see there, we tried to save as much rebar as possible because we're going to have to put it all back and reconstruct it. But to gain access to those piles, we had to do a lot of demolition. This is what the work area looked like from up top. So you've got a barge offshore of the wharf itself, but it gave them enough room to put a small excavator in there with a hoe ram to do the demolition, as well as the power packs and everything for the hydraulic hammer. So Cape Romaine contractors did this testing for us. In the construction, they used a J&M ICE 220 hydraulic hammer, which had a 3.5-foot stroke, 22 kip ram, which resulted in an energy of 77,000 foot-pounds capacity. So we did PDA testing using that hammer, and what we ended up finding was the data that you see in front of you. Basically, with the Cooper Marl, primarily, you've got usually in between like 80, it's like the 80-20 or 90-10 sort of split in between side friction and end bearing. And we were that sort of rule of thumb sort of held here as well. But we had a pretty substantial capacity confirmation, if you will, during this testing. As you can see in the lower right corner, we had a bearing capacity, ultimate bearing capacity that we mobilized of 677 kips and 642 kips in that 18-inch pile, which is good because we had lower capacities that were on the original design documents, which we'll talk about in just a minute. So that testing was really important. The other thing to note that we ended up using is that the upper left corner, the displacement versus load, that pile stiffness, the axial pile stiffness, was also something that we used in our analysis to really help us out later on, and I'll talk about that in just a minute. So similarly for berth 3, we used the same hammer and barge setup, and we also got to the top of those 24-inch pre-stressed concrete piles, and we're able to mobilize capacities in between 975 kips and just over 1,000 kips in each of those piles. down on the other end. You can see the same distribution of side friction and end bearing in those piles as well. So as I mentioned, we couldn't take the ship to shore crane rails out of service. So what we had to do is, since we picked the middle piles or something close to the middle, we ended up having to extrapolate, if you will, the capacities of new and existing piles underneath those ship to shore crane beams. So if you look off to the left, you'll see blue and green piles. Those will be the piles that actually resist the ship to shore crane loads. The crane rail above those piles was also ended up being reconstructed because of structural issues. But the foundation itself, we had to sort of extrapolate our test pile, which is the red in the middle, to the waterside and landside situations. So we considered a number of different things, you know, overburden. You can see the one on the land side has a lot more overburden over the stiff clay than the water side does. The marl embedment, we knew the marl embedment we had a good idea of the marl embedment from installation logs of these piles. So we could use that to sort of extrapolate the capacities for new piles. We also had to consider pile proximity. As you look at the water side, and I'll explain more in just a minute, but you know, we had a lot of other piles around these, new ones that we're going to install, as well as existing piles. We had to consider that. And we also had some variation of the elevation of the actual marl along the length of the wharf. We had to consider that in all of our analyses. So what you'll see here is an allowable pile bearing resistance comparison in between sort of where we started in design and where we ended up as a result of testing. So in the upper table, you'll see that we had, for those 18-inch piles, the initial allowable bearing resistance based on information used in the initial design of the wharf, you know, those piles, the allowable bearing resistance was only 160 kips. Similarly, for the 24-inch piles in berth 3, it was higher, but still not huge numbers here. If you look at the revised allowable pile bearing resistance range off to the side, and that range is because of the pile embedment changes as you go along the length of the wharf and the variation in the marl depth, you'll see some pretty substantial differences there. You got, you know, 50 to 78% increase, 73 to 96% increase, 83 to 119% increase. Similarly, for berth 3, we saw some pretty substantial resistance increases in between, you know, 450 and 600 kips as a result, going up 41% and 88% as a result of just this testing. So having done this testing, we had a very valuable tool in our hand to move forward in design. I'll tell you more in detail about what that did for us in a second. But when I said I was really, this can be a very nerve-wracking material to deal with. If you look at the bottom portion of this slide, it says side note 1 day versus 14-day versus 21-day PDA restrikes for ongoing composite pile driving. So whenever we were actually doing this construction, we took note of this. And at the end of initial driving, just on this one pile, for instance, we had we had 4 blows per foot was where we stopped driving that pile. And as a structural engineer, it always makes me very nervous just about how low resistance that seems like. But we know through all this testing that resistance actually goes up with time. You can see that as a result. So the end of, if you look at the bottom number, for instance, this is the same pile, but basically a month later, we tested it at 7 days, and then we had to wait and test it at basically a month, which is another 21 days after the initial driving. You get a resistance at the base of 6 blows per 1 inch, and a pretty substantial increase in the capacity of the pile. And these are different size piles and whatnot, but I wanted to show you that at the end of driving, the marl doesn't have that really high end bearing resistance. It takes time for the clays to remold around it, but you do get that set up within 14 to 21 days that ends up getting you into the capacities that we tend to use. So what we did with this information, as I mentioned, is we were actually able to use the existing axial pile stiffnesses to our advantage, if you will, because before we didn't really know how stiff these piles were. We thought they were a lower capacity, but using those existing pile stiffnesses, we're able to sort of optimize where all the loads were going and get a better idea of what was actually going where. With that information, So with that information, as well as the extrapolations like I was talking about earlier, we were able to optimize our new production pile lengths, which, as you know, that's also a good bit of money there. If we're able to have a higher confidence in our numbers, we actually were able to help reduce some production pile lengths there. And just some rough numbers, we were able to reduce our waterside piles from initial design to final design by 40%. And same thing from the land side, we were able to reduce our number of piles there by 12%. That's just a total number of piles, not even looking at pile length. And burst 3 was really the winner from all this testing. Again, we were able to use the existing axial pile stiffness a little more effectively to get the load sharing done right. And our revised capacity said that we didn't need any new piles in this berth, even with the increased ship to shore crane loads. That was a really exciting day for us because we knew we had to do some local strengthening of the crane beam as a result of just the higher wheel loads, but to not have to drive any new piles in this berth was a substantial win for us. There's a substantial amount of reduction and demolition of the existing structure and the downtime there that we'll talk about in just a second. So again, if you look at the total number of piles in berth 1 and 2, so pre-testing, we were planning on needing 592 piles, and post-testing, we ended up with 361 with a 40% reduction, as I mentioned. And again, in berth 3, we were planning on over 336 new 24-inch pre-stressed concrete piles along those crane beams, and we ended up with 0. That was like I said, that was a very good day to receive that news. So just to give you a frame of reference, we had an estimated construction cost savings. We spent about $275,000 on the testing program. That's about 0.4% of our overall construction budget. And when I say budget, that's actually what we spent, the 0.4% number. And we ended up with what we're estimating is $9 million in construction savings. Most of that is the piles themselves, but also there's a lot of demolition that we did not have to do, particularly in berth 3. That this testing program saved us. And not only was it pure construction dollars, it was also it's a very hard number to quantify for our operations, but we originally estimated the project to be about a 32-month project. That's renovating from one end to the other of the wharf over those 3 berths, 3,800 feet. We believe we realized over a 6-month savings in having a berth offline. I'll show you that in just a second. There's a 19% reduction in just the construction duration. So just to give you sort of a timeline here, we started in September of 2015. We had to do different phases of construction because we couldn't shut the entire wharf down all at once. We had to keep doing business so we could spend money on construction. Phase 1 was only 600 feet. We finished that in May of 2016, and that 600 feet was very specific because we had those 2 new ship to shore cranes coming online. We brought those into that phase, and that's where they sat for a while they were being commissioned. We finished phase 2 in December of 2016. And as you can see, we sort of marched all the way down, getting 2 more cranes in March of 2018. And then by May of 2018, we were substantially complete with the entire length of wharf. As I mentioned, whenever we're doing this renovation, we essentially had to shut down a berth. So anytime you shut that down, that means the ship can't come in there. That means they can't bring in containers to the facility, and you're losing money every time you're down, every minute that you're down. So that construction savings, like I was talking about, that 6 months is really hard to quantify, but I can guarantee you it's more than we saved more than the $9 million we saved in pile testing or the pile cost that I mentioned earlier. So this is just showing you some construction photos of where we brought in the piles. We actually used composite piles whenever we went back. We did have some issues that we knew of from the early 90s construction of berth 3 with the 24-inch pre-stressed concrete piles bouncing a little bit in the stiff clay layer. So we actually used composite piles here. But with PDA testing and everything, for these production piles, we were able to confirm all of our assumptions that we had in the initial testing program. So we installed over 410 piles with a total length of over 40,000 linear feet of pile. So in concert with all that pile installation, we had a lot of other things going on. We had to replace bollards, do selected concrete demolition, rebar placement, concrete placement, and crane rail placement. We installed over 75 7,560 feet of 175 pound per yard crane rail. That's the largest Buy American compliant crane rail that's domestically available from one end to the other. So that was a pretty interesting part of the project as well. And then, as I mentioned, we were substantially complete in May of 2018. You can actually see in the middle there, those are two of our new, at the time, ship-to-shore cranes being developed. That was a very interesting process to get this moving forward through that phase construction on an active terminal. Like I said, it was a really interesting project. But some of the things that we came up with here is that, what we showed here in this presentation was a dynamic pile testing of existing pre-stressed concrete piles founded in the Cooper Marl Foundation. The in-situ testing used to determine the as-built compressive capacity and stiffness of the piles for larger working loads and load sharing was very key here. We used both of those, not only just the actual capacity of the piles, but also the stiffness to really refine our design and save some money there. And as I mentioned, we had some minor operations disruption during those 33 days and 74 days areas whenever we're doing the pile testing, but it resulted in over $9 million in construction savings. And it's really hard to quantify this, but I can guarantee it's more than 9 million. But that 6 months of construction duration was 6 months of time that we were able to bring in containers through an active berth, and that was a very big win for us. So with that, I want to thank you for your attention and your time, and I want to also thank sort of co-authors on this study, Greg Canavan and Billy Kemp with SNME, and I will open it up for either questions or we can go from there.
Thanks, Ed. Thank you for a very interesting presentation, and obviously clear indication with numbers that increased testing that save money. What I would ask you to do now is just turn on your webcams, and Carol, if you could just stop sharing the screen so that the people watching this webinar no longer just have to watch this stagnant screen. That would be very helpful. The first question that I have, and it's a question that I ask everybody that is presenting during this webinar series, something very simple. You've indicated that increased testing does save money, and in your cases, but it is still something that a lot of people in the industry don't necessarily accept or not necessarily implement in their projects. Given your experience, because you've together been quite a few years in the industry, what is it that we can do to really make sure that this concept of doing more testing, whether it was what Don was saying, doing testing up front or doing more testing in general, what can we do to really get that message better accepted, better ingrained in project execution, so that in a way we no longer need to have a webinar series on this topic? And let me, Kevin, start with you.
I think case studies like these are helpful to be able to go to clients and tell them times that previously you've been able to implement testing in advance and save 20%, 50% on a project. So certainly having examples like this in our own previous experiences, but also just being aware of other references when advanced testing has helped is definitely valuable.
Okay. Don, your views on this?
You need to get facts and decision points, make it easy. Who's the decision maker, and get the information in their hand that lets them validate what they're doing. So it's make the business case. If it's in many cases, if you want to be advocating to the engineers and the design community, put the information that in their hands that they can take to their clients that makes them look good. Show them how through being a smart engineer that does more testing, they can help an owner save money. Make that business case. I talked about bringing carbon into the conversation, but people are motivated by risk. They're motivated by value, and that value can, that can be carbon, that can be dollars. Make that business case, put the information out there to enable someone to show value or show that they are reducing that risk.
Okay. Ed, anything that you would like to add?
Yeah, I think that Kevin and Don both had really good answers to this one. And the only thing that I would add is that we are using this approach more often in our future designs of terminals. We just finished the development of the Hugh Leatherman terminal just across the river from us, and we used pile testing. We had a pile testing program in advance of the construction project, knowing we'd need time, but we knew that it would pay out for us along the way, both in reducing risk, like Don was mentioning, but also time for not only construction, but also we're able to evaluate our pile lengths and get those nailed down early on to sort of reduce some construction risk for the contractor. Because going into a testing program with index piles, for instance, if you've got 4 or 5, your capacity is based on those, and you're basing some of your production links on those, and you may have some increases for like pile buildups if you have to drive something long. So we definitely see the advantage of doing this, and we're using that on all of our future design projects well in advance. Like Don and Kevin were both mentioning, we have the time. We're going to try to use it more to our advantage up front in the job to get some of this testing done to hopefully save ourselves on the back end.
Right. Talking about
Can I add one other section
Sure.
thought on
Right.
that? Because it would be interesting to change the narrative a little bit. We always tell our success stories, right? We always show the pictures of what we've done wonderful, and we can talk about how we save money by doing this testing. And it's sometimes harder to get the information, but we should talk more about, create more case studies, as Kevin was talking about the failures, about the things that didn't go well, why they didn't go well, how could testing help mitigate or prevent that? Because when someone starts to understand, oh, that pile failed and that cost a project $5 million and 18 months of schedule before they could fix the problem. It doesn't take many of those to sway someone that, tens of thousands of dollars of some testing sounds like some pretty cheap insurance policy up front.
I fully agree with you, Don. And I cannot tell you how many times I have approached a contractor or an engineering firm to say, hey, we have this webinar series, and this situation where you had this failure would be perfect illustration why you need to do more testing. Are you willing to give a presentation? And then so always is, not really. We can talk about something where it went well, but to show this. So if you or anybody else in the audience can come up with some case studies like that, I would love to have them incorporated, because indeed it's another illustration of why testing makes sense. Going slightly in a different direction, I was kind of on the two presentations as I looked at your slides. Kevin indicated in his presentation that there was a clear incentive for the contractor to reduce the time that the bridge was closed. $25,000, I think, a day that he mentioned. Ed, in his presentation, clearly indicated, hey, those 6 months of shorter schedule saved a ton of money. Any further information that you can share with us about the actual values? Kevin, at the $25,000, was that just a number kind of to put something in the contract to give an incentive, or was it based on some data analysis that you have? And then for Ed, after that, could you give some indication? You already implied that the 6 months saved more than the 9 million on the materials, but can you give us an order of magnitude what that saved? Kevin, first with you.
Yeah, I think the $25,000 per day was largely based on user costs. Each day that the bridge was closed, the driver's going to have to use a detour, and pretty much determined approximately what that would cost per day and put a dollar amount to it to incentivize the contractor to get done earlier.
Okay. Ed?
Yeah, so we actually, Kevin mentioned they had bonuses on their job. We actually had liquidated damages on our job of $25,000 a day. And I can tell you that's not even half of probably what the worth is of a berth per day, depending on the vessel coming in. So, you know, I say that, you know, we had that $25,000 in liquidated damages, and that's not even, that still doesn't cover the revenue that we would lose per day at a berth. It all just depends on how many containers are coming in and going, but that's something that we did put in there. We didn't have any bonuses because we didn't know, there was some variability there, but we did have liquidated damages there of that 25,000 a day. And again, that's a low number that doesn't cover what we would lose per day if they were late. But it gives you an indication of what was saved by that 6 months of construction time.
So 6 months, roughly 180 days, $25,000. What is it? Something like 45 million? Yeah. That's,
Yeah, I mean, it's the dollars add up very quickly.
yes, definitely. There have been a couple of questions in the question box from the audience, and for all of you still there, please don't hesitate to keep adding those questions. I think the one question that hasn't been answered yet is a question for Ed about the testing there. How do you adequately separate the side friction and end resistance of driven piles just by PDA? As shown in the interpreted results, significant resistance difference between the soil and the marl bedrock. Are the interpreted load distribution percentages realistic?
I could speak mostly to, as a structural engineer, I couldn't tell you everything about how we got to those numbers. What I will tell you is that we do have good rule of thumb numbers around as far as side resistance versus end bearing. And especially with our composite piles that we were using going in, we knew H piles at the tip, so it's a very low end bearing area. So we were relying mostly on side friction. So the results that we saw were something that we were expecting. And I can, if I get your information, I can send you off to the folks at S&M to talk a little bit more about the details of how they determine the difference in between side resistance and end bearing. But our piles, particularly with an 18-inch square, 24-inch square, most of the embedment is where you're going to get your resistance in the marl. And most of the overburden didn't provide very much resistance for us. There was some areas where it did, where there was some gravel from a previous, or from how they constructed the wharf, but by and large, the results that we saw from side resistance and end bearing were what we expected.
Okay. Kevin, going back to your presentation, you talked about the project that is, but happened about 10 years ago or so. Since then, you slept a little, and quite a few things have happened. Looking at it right now, would you have done things differently? Are there learning points where, based on what you have done then, what you did then, how you would do things differently now, or in the same manner, are there things that what you did there have been applied on other projects in the area, so that there's an evolution of how things are being approached?
No, my answer probably won't be great. I think anything that would have been done differently probably would have been more in the upper parts of the bridge and the truss. I think as far as reusing the foundation, that went about as well as it could have. I mean, it's 10 years later and the project's been a success. We were certainly able to save the money and get the project done quickly. I mean, certainly years ahead of what it would have been done if we were building a new bridge. I don't know that those, at least for any project I've been involved in, that those exact methods have been reused on other bridges. I mean, certainly in Ohio River Bridge, we don't do a lot of those projects every year or so, especially reusing piers that have been 75 years old. So I'm not aware of immediate reuse of any of the ideas I presented today.
Okay. One question that came in from the audience for Ed, why the water side has higher savings of 40%?
Yeah, so a lot of times, or what we were doing on the water side, we were having to, or what we planned on doing initially during construction was adding 2 piles between each pile bent to supplement the beams that were already in, supplement the piles that were already in place underneath the crane beam. What we were able to do by the pile testing, it actually allowed us to go from having 2 piles in between each bent to 1 pile between each bent. So as a rough number, it was 40%, but we had to keep those 2 piles in between each bent and each tie down location. So for service and operating loads underneath the ship-to-shore crane, we're able to take out 1 pile per bent. That's where we ended up with the 40% there. But on the land side, we weren't able to do as much because of the inherent service loads and the heavy back reach area of the ship-to-shore crane. So we had a closer idea of what we needed on the land side than we did on the water side, but that's where we saw most of our savings was on the water side.
Okay. Don, coming back to similar question I asked Kevin before. Obviously, the message on carbon content and the way you could save carbon has been something that has been near and dear to you for some time. You've been preaching this promoting this. Whether you're preaching or promoting, leave that up to the audience. But you've been bringing this message. Do you see a change in acceptance? Do you see that people are starting to believe more in it, are responding more easily to it, or is it still over the last 5 years not much it has changed in that regard?
It is a absolute tipping point watershed moment that's happened, I would say, over the last 2 years. I'd say there's been 10 years of a conversation that has been in a very niche group of people who really wanted to have the conversation. I just was flown down to Houston and spent an entire day with a development company and 30 other senior executives saying, how do we bring this to what we are doing? A lot of it is driven by, in our case, there's a lot of commercial work. The tech tenants, the tech clients are all clamoring on this topic. And there's both a lot of money that they're putting into funds to try to somehow be addressing climate change in the built environment. And the developers I was just talking about, they are super keen on their investment portfolios, where they get their money from. And the big buzz from all the banks is ESG. What is your ESG? What are you doing about ESG? And the E on that is environment. And they're looking at metrics. They're looking for the value stories, and who's being progressive to drive solutions forward around climate change. And it's becoming something the developers need to show what they are doing in this space to get money from the banks or get money from the lending institutions or whoever they might be. So there's definitely a trickle down happening there, but there's conversations on this happening at levels in rooms I never expected to be in as the structural engineer who I'm talking to about embodied carbon. The faster I think the construction and design community have responses and answers to that, it's the difference on who's going to get the work, especially at least in the private sector. In the public sector, I would say this, now Build Back Better, I know it hasn't passed, but there was, I'm trying to remember the number, there's multiple millions of dollars in that for EPDs, environmental product declarations, and to put a system in place that the federal government would administer, asking for EPDs from suppliers as a way to kind of monitor and track what's going into the build out of and frankly, the repair and fix of our aging infrastructure. Yeah. The questions are going to get asked. Yeah. I'm seeing legislation across the country and called Buy Clean legislation that's passed in at least 4 states, and there's many more talking about it. So it's a freight train that's coming.
Yeah, no, it's. I recently attended the annual conference of the Transportation Research Board, and it was amazing how much more they talked about sustainability and carbon content, carbon footprint compared to previous years. So I fully support what you're just saying.
If I put it in an easy way, carbon and dollars is just treat them the same. It's just another way to talk about the same variable. Mm-hmm. And the more they get treated similar, the easier it is for us to bring into a narrative how we talk about it. but to bring it into the conversation.
Yeah, fair enough. I don't think we have any more questions. Sorry, did somebody? No, I hear an echo somewhere. I don't think there are any more questions right now. So I want to thank all of you for your presentations. I think, as was mentioned earlier, it's a nice range of different presentations that illustrates this topic. But I appreciate very much that you were willing to present these projects. I also want to thank our audience, and Carol, if you could put the slides back on for a second. For those of you that are interested in more case studies, as I told you, this is the 15th webinar that we're doing this series, and we will continue with this series, as you see on the screen right now, in the first Wednesday of April and the first Wednesday of June. That went through fairly quickly. One back, Carol, if you could. But we always have this on the first Wednesday of the month at 11 o'clock Eastern time. And obviously in April and June, it will be 1 o'clock Eastern Daylight Time. If you have any topics that you would like to suggest for this, please let me know. We can always use topics for this. And also, as a follow-up on this whole thing, you will get a PDH certificate. Normally, we try to get these out in about 3 weeks after the event. And if you have any problems about the PDHs, or if you need more information, you can either contact me or Jamie Satina. You see her email address on the screen, jsatina@dfi.org. Finally, I want to suggest that if you want, as a company, want to sponsor this, that's an option as well. And you saw something there about the sponsoring capabilities. Either talk to me or to NG Gibble at DFI to get your commercials played before and after these presentations. And with that, one more time, thank you to our 3 presenters for today. Thank you for the audience for being here. And I look forward to seeing all of you again in about 2 months for the next edition of It's Money. Thank you very much.
Thanks, Gerald.
Thank you.